I'm Tommy Gores. The thought of colonizing Mars has been within our imaginations for the past century. Books, articles, and even programs such as SpaceX have been dedicated to the exploration and the colonization of Mars. This leads to the question, to what extent is colonizing Mars feasible? And through our research, we will delve into the reality behind colonizing Mars. Mars has already been explored in literature such as The Martian Chronicles, The Sands of Mars, The Martian Way, The Stranger in a Strange Land, and most famously, The War of Worlds. In War of Worlds, the Martians come to Earth and almost destroy humankind. However, in reality, the opposite is almost real. Instead of Martians coming to us, we will go to them, and we have positive outlooks on Mars. In the book, How Do We Colonize Mars by Matt Williams, he delves into the reality of what it really takes to colonize Mars, the economics and the physicalities of what is required of going to Mars. As we have already traveled to Mars in the 20th century, and in this century, NASA has sent rovers to Mars that has explored the geographic regions and locations of Mars, and has brought back samples, images, and information that is necessary to our planning of colonizing Mars. And this colonizing of Mars has been proposed by Elon Musk, the CEO of SpaceX, which is an American aerospace company. They've already explored and researched rocket technologies, which is essential to going to Mars and the travel to Mars. He has proposed sending colonizing parties to Mars by 2030. And this colonization of Mars would just be an extension of the historical colonization that we've already had in the past, such as the Age of Exploration, where the Spanish Empire and Great Britain had set up colonies in the New World.
Our group decided to go past the fiction involved with colonizing Mars and just proposals. We wanted to see how is colonizing Mars truly feasible. The definition of feasible is possible to do easily, conveniently. So, is colonizing Mars truly feasible? So why Mars? Why has this planet, out of all of them, been chosen for colonization? It is simply because the transition from Earth to Mars is the simplest of all the planets. For example, the day length of Mars is only 40 minutes longer than on Earth. This makes transitioning from an earthly life so much easier for all of the humans. It also has similar seasons in farming. This also relates to day length because it is much simpler to grow crops. The atmosphere is thick enough to protect crops from radiation. Also, the natural resources such as carbon and hydrogen create luxuries possible for a modern society, such as electronics. It has the possibility for wind energy, and the natural resources could be used to produce a viable economy.
So obviously there are going to be a few obstacles to overcome since this is interplanetary travel. There are three things that we need just to function as human beings. That would be food, water, and oxygen. Mars has really none of that, so that's going to be an issue. The temperature is also pretty tough to deal with because it's not exactly similar. It's actually pretty different from Earth's. There's radiation, gravity, fuel costs. We'll be going into this a little bit after. So food sources. We've actually have done tests on samples of soil from Mars. We've taken samples from the planet itself and from meteorites, and we found that there are actually micronutrients and macronutrients in the soil, which could support growing food. It's somewhat fertile. However, obviously, it'll change the ratio of how many micronutrients and macronutrients will change depending on where they land or where they are on Mars, but it's nothing a little fertilizer can't solve.
One of the easiest obstacles to overcome is the water sources. There's already a ton of water on Mars, however, it is frozen at the polar ice caps. Part of solving this would be raising the temperature of Mars, which would melt the water. But there's also natural resources of local water all throughout the planet hidden underground. We can tap into this, but to off-put the amount of water that we would have to take from the ground would be a recycling system that we've already pioneered and implemented in the International Space System. There's a recycling system which uses our urine and sweat and turns it into drinkable and usable water. The levels of oxygen, however, are completely different, and the atmosphere composition of our atmosphere and Mars's atmosphere are entirely different. Our atmosphere is about 70% nitrogen. However, Mars's atmosphere is about 95% carbon dioxide. And there's only traces of oxygen within the atmosphere of Mars, which we need to live. So raising the temperature would help solve this problem by melting a lot of the water at the polar ice caps and restore Mars's historic oceans. By restoring the oceans, we would promote more oxygen in the atmosphere, and to create a more sustainable atmosphere like Earth is to put more nitrogen into the atmosphere. One way to do this is importing ammonia ice from other planets and moons, and by importing this ammonia ice and melting it, we would diffuse the nitrogen in the ammonia ice into the atmosphere. And this is all called geoengineering, or also known as terraforming. And this terraforming would also be used with cyanobacteria and phytoplankton, and would convert more of the carbon dioxide in the atmosphere into oxygen, which is one of the theories of how Earth's atmosphere originally had gained more oxygen.
Another factor that has posed future threats for colonies on Mars is the temperature. It is pretty inhospitable, to say the least. It is known as a bipolar temperature because through midday it's normal, it's about 68 degrees Fahrenheit, and as you get into the evening, it gets extremely, extremely cold. And this is only around the equator. So on the poles of Mars, it is very, very extreme and a lot more cold and a lot more hot during the day. So colonies would have to deal with fluctuating and inhospitable temperatures, and this would result in special shelters and special suits, and it would increase the difficulty of living on Mars. Radiation, this is also a huge factor that we have to overcome. When Earth and Mars are the closest, so it would be a 9-month trip to Mars. So colonists would have to travel on a spaceship for 9 months. During this time, they would experience about 0.66 sievert of radiation. This increases the chances of cancer extremely. This also not only affects them, the colonists themselves, but it affects their future posterity. Radiation causes fertility issues, and the likelihood of cancer is increased. This makes it very difficult to sustain large populations and colonies on Mars because they're dealing with this constant radiation.
Okay, so there are two different types of radiation. The first one comes from the sun, and those are energized solar particles, and they're not quite as dangerous as the second one because they can be filtered out by the spacecraft itself. The second ones are called galactic cosmic rays, which are really, really dangerous. They come from different galaxies and solar systems in our universe, and they're so dangerous because they're really, really energized. They can accelerate near the speed of light, and oftentimes they are mixed in with a few heavier particles, which it can allow them to penetrate the spacecraft. And if they can penetrate the spacecraft, then the astronauts and the colonists will be exposed to all this dangerous radiation. And radiation is so dangerous because if it can penetrate human skin, then it can penetrate muscles, tissues, bones. Depending on what type of radiation it is, it can penetrate at different depths. However, it can cause damage to DNA, which leads to cancer. And another setback would be radiation sickness, which is fatal. It's really fatal. It wasn't as common. It's not as common on Earth because, as Aubrey said, the atmosphere will filter out all the radiation. But in deep space, if they are exposed to it for prolonged periods, they can get radiation sickness, and with the symptoms being nausea, headaches, disorientation, bloody vomit, bloody diarrhea, and then you die. So you don't want that. So you can protect yourself from radiation, and in layman's terms, you can just block it with a particle that's similar in size. And a particle that is similar in size is hydrogen, which conveniently is actually the most abundant element in our universe. Water is really, as you guys know, is made up of hydrogen. So since water is already necessary to bring on the trip to Mars, they've proposed an idea where maybe we can sort of place it, instead of storing it in just one area, we can sort of place it where it would shelter out all the radiation. That's not exactly ideal. Another option is polyethylene. It's just a really common plastic. You guys know what polyethylene is, and it's also sort of rich in hydrogen. However, it's not very sturdy. It is plastic. It'll melt, and when you're in space, there's a lot of heat, and traveling as fast as you are, that would also bring on a lot of heat, and it wouldn't be able to withstand it. And it's also really, really heavy, which affects the fuel, which I'll get into in a bit. The ideal solution is what we call hydrogenated boron nitride nanotubes, and these are really, really cool because they're just nanotubes made up of boron and nitrogen, and they're hollow. They're tubes. So you could implement them into the structure of the spacecraft itself, and you could put hydrogen, and that would block out all of the radiation. And another plus would be boron is actually a second line of defense because it also is really, really good at filtering out all this radiation. Now, what's cool about hydrogenated BNNTs, I'll just call them that for short, is that they can be spun and woven into fabric. So then you can make potentially suits out of this, as opposed to just lining them in the spacecraft. You can make suits for them, and they can also be made into structures which they can use to build buildings on Mars in lieu of an atmosphere. And another, they just give hydrogen structure because hydrogen can exist as a structure itself. It's just an element. It can protect them, and it will use these nanotubes as a medium. Another option is terraforming, which Tommy mentioned before. Terraforming would pretty much solve all of our problems, really, because if you terraform, if you heated up the Mars's atmosphere or its surface, it would melt all the frozen water, and that could give us oceans, but it would also give us some pretty thick atmospheres, or it would give a thick atmosphere which would sort of replicate Earth's atmosphere. Another important part is fuel. Now, you have to understand how fuel works first. There is something called specific impulse, which it is really just a measure of how efficient it is. It's just how much it can accelerate using one per unit expended. So let's say there's fuel A and fuel B. Fuel A can make it accelerate, let's say, just for this purpose, 5 kilometers per second faster than fuel B. Fuel A would have a higher specific impulse. Another thing you'd have to take into consideration is thrust. Now, thrust is important because it's pretty much specific impulse, except when it's measured, the atmospheric pressure is factored into it. So on Earth, you'd need a fuel with high thrust to get it off of Earth's gravity. But in space, because it's sort of a vacuum, you really just need something with high specific impulse. Now, density is another factor because fuels with high density often have high specific impulse. So that means that it has high thrust. So that would be ideal for phase 1, which is liftoff. The second fuels with low density. They are often liquid, but they have really, really high specific impulse. Kerosene is really, really dense, which means it's really good for the phase 1, which is just liftoff. However, it's really expensive. These are a few options, which is kerosene, which again, used for stage 1. Oftentimes, hydrogen and oxygen are used for interspace travel because it's high in specific impulse. But in this specific voyage, the ideal fuel would be deep cryogenic methalox because that, again, has high specific impulse, and more importantly, it can be mined on Mars. So if they didn't have to bring the return fuel with them, that would lighten the load a lot, which would lessen the requirement for kerosene.
Okay, I'm sorry to interrupt you guys. You are at over 14 minutes. Do you have a lot more?
No.
Well,
Okay, so carry on.
Okay. Ticket price, it's pretty expensive, $10 billion per person. However, reusability is a big one. The average 747 Boeing is $357. I bring that up because if it wasn't going to be reused, then they'd have to pay that $357, but it is reused. So now you can even buy tickets for as low as $42 per ticket. Next slide.
The gravity on Mars is substantially different than the gravity here on Earth. The gravity on Mars is only 40% of what Earth's gravity is, which would lead to if you were to stay on Mars, would lead to 5% muscle mass degeneration a week and 1% of bone density loss a month. And prolonged periods on Mars would lead to osteoporosis and muscle degeneration in the colonists on Mars. And if you were to go back to Earth from Mars, you would most likely die on impact because of your brittle bones and your inability to support yourself. The political system would also be substantially in conflict. Whoever, or the colonists that take a ship to Mars, wherever the ship is originated from is where the laws that the colonists would have to abide by. So if Russia were to implement this colonization of Mars as well, and along with us, then the Cold War could be reversed potentially.
Overall, we decided that colonizing Mars is possible, but it is not feasible. We need to focus on overcoming these obstacles before we can even think about colonizing Mars within the next 30 or 40 years.
So that was 16 minutes. So about double, FYI. All right. Tommy, describe how the content of the team presentation was changed as a result of group discussion.
Group discussion led to a lot of my research not being implemented. My research was a lot of historical information, and a lot of this solution was looking towards the future. And my research was involved with the political systems and the background and the understanding of the whole picture. But as far as the entire group, my lens was not as important.
Aw. Aubrey, what was the strongest counter argument to the solution or conclusion that your team identified, and why?
Strongest counter argument. There were several counter arguments, as you saw from our presentation. I think that gravity is one of the major factors we have to overcome because it can't be manipulated as the other ones can. So when you are already a nutrient deprived colony because you can't get enough to sustain your life pretty much, now you're dealing with muscle degeneration and osteoporosis and cancer because of radiation. So gravity really can't be manipulated as well as temperature could be.
Okay, thank you. Bobby, having finished your project, what, if anything, do you consider to be a gap in your team's research that, if addressed, would make you feel more confident about your conclusion?
I think overall we got most of it, I think. Well, I mean, we could have gone a little more in depth on a lot of things. Not a lot of things, but I guess gravity, because, there really is no solution. So, I mean, our potential research really was limited because all the other ones, although they would be tough fixes, they are fixable, whereas gravity, can't really do that, but I guess gravity would be the answer.
Okay, thank you.